In this video, we're going to talk about uncertainty, specifically absolute uncertainty, relative uncertainty, and also percent uncertainty. So let's say if we have a book and we wish to measure the length of the book. Using a ruler, we estimate that the measurement is 25.4 centimeters. Now we're fairly certain that it's about that much, but we're not precisely sure. So we're going to add our estimated uncertainty, which is going to be 0.1. It's based on the last digit. So if your measurement rounds to the tenths place, your uncertainty will be one significant digit in the tenths place. So in this case, 0.1. So this value here represents the measurement, or the measured value, and this value here is known as the estimated uncertainty. It's also called the absolute uncertainty. Now, if we wish to calculate the relative uncertainty, it's simply the estimated uncertainty, or the absolute uncertainty, divided by the measured value. So it's 0.1 divided by 25.4. So let's see what that comes out to. So that's 0.003937. So that's the relative uncertainty. Now, to calculate the percent uncertainty, we simply need to multiply this number by 100%. But here's the formula for those of you who are interested in it. So the percent uncertainty is going to be the absolute uncertainty divided by the measured value times 100%. So in this case, it's going to be 0.1 divided by our measurement, which is 25.4 centimeters. By the way, both of these numbers are in centimeters. And then times 100%. So it's going to be what we see here times 100, or if we move the decimal 2 units to the right, we're going to get 0.3937%. So that's how you can calculate the percent uncertainty. Now let's say we have a graduated cylinder with liquid inside of it, and we want to measure the height of the liquid, or rather the volume of the liquid. Now let's say when we look at it, it looks like it's 18 milliliters. If we're given this measured value, what is the uncertainty compared to if we have, let's say, 18.3 milliliters or 18.34 milliliters? What should be the assumed uncertainty for each of these measured values? If our measured value is 18 milliliters, then the uncertainty is going to be based on the last significant digit. So notice the 8 is in the ones place, so our uncertainty will be the lowest number in the ones place, which in this case will be 1. So that's how we can determine the assumed uncertainty given the measured value. Now, if our measured value was 18.3 milliliters, our uncertainty will be based on this number. It's going to be rounded to the tenths place, so it's going to be 0.1 instead of 1. So that last 0.1 we're uncertain. The volume could be 18.2, it could be 18.4. Now, if our measured value is 18.34, then the uncertainty will be based on the last digit. So it's going to be 0.01 milliliters. Now let's work on some practice problems. The volume of fluid in a graduated cylinder is 46.5 plus or minus 0.1 milliliters. Determine the relative uncertainty. So in this problem, we're given the measured value and the estimated uncertainty, or the absolute uncertainty. So to calculate the relative uncertainty, let's call it RU. It's going to be the uncertainty divided by the measured value. So the uncertainty is 0.1, the measured value is 46.5. And that's going to be 0.00215. So that's the relative uncertainty in this problem. Now let's move on to part B. Calculate the percent uncertainty. So the percent uncertainty is just going to be the relative uncertainty times 100%. So it's 0.00215 times 100. So that's going to be 0.215%. So that's all we got to do in this particular problem. Number 2. The length of an eraser was measured to be 5.4 centimeters. Estimate the percent uncertainty in this measured value. In this problem, we're given the measured value but not the estimated uncertainty. So we need to assume its value. So we can see that the last digit is rounded to the tenths place. Thus, our estimated uncertainty is going to be in that vicinity. So the best number to pick, the lowest number to pick, is going to be 0.1 centimeters. So that's our estimated, or our absolute uncertainty. Now that we have that, we can calculate the percent uncertainty. So that's going to be the absolute uncertainty, which is 0.1, divided by the measured value, which is 5.4, times 100%. So that's going to be 1.851%. So that's what you can do if you need to calculate the percent uncertainty, and if you're only given the measured value and not the estimated uncertainty. Now let's work on this problem. Determine the percent uncertainty in the volume of a sphere whose radius is given 5.24 plus or minus 0.07 centimeters. So we're not trying to find the percent uncertainty in the radius, but in the volume. How can we do this? Well, first let's begin with the volume formula of a sphere. It's 4/3 pi r cubed. Now, the radius, we have a range of values that the true radius could be. The radius could be 5.24 minus 0.07, in which case the lowest value will be 5.17 centimeters. Or it could be 5.24 plus 0.07, so the highest value of r is 5.31 centimeters. So we're going to plug in the lowest value of r, the measured value of r, and the highest value of r to see what the volumes will be. So let's start with the lowest value of r. So it's going to be 4/3 pi, and let's plug this into r, times 5.17 raised to the third power. 4 pi times 5.17 cubed divided by 3. That works out to be 578.842 and this is going to be cubic centimeters. So that's the lowest value for the volume that we have. Now let's get basically the middle value, or the value that's based on the measured radius. So we're going to plug in 5.24 instead. And let's use the approximately equal sign because this is not an exact answer, but an estimated answer. Thus we have 4 pi times 5.24 cubed divided by 3, and that's going to be 602.674 cubic centimeters. Now let's get the highest value for the volume that we can get using the highest radius value of 5.31. So that's going to be 627.151 cubic centimeters. So now let's take the difference between the highest value and the measured value. So if we subtract 627.151 minus 602.674, we're going to get 24.477. Now, if we subtract 602.674 by the lower number, 578.842, that's going to give us 23.832. Now, here's a question for you. Which of these two values should we use as our estimated uncertainty for the volume of the sphere? Should it be this one or this one? If we were to use the lower one, 23.832, this number will be included in a range, but this number will be outside of the range. Because if you were to add these two numbers, you're going to get a number less than this. So to make sure that we get both values in the range, I like to choose the greater of the two values, because this will give us the highest value, the highest volume, and also it will overshot the lowest volume on the other side as well. So I'm going to use this for the estimated uncertainty. So thus we could say that the volume is 602 point. Now I'm going to round this to 0.7. 602.7 plus or minus, and I'm going to round this to 24.5. 24.5 cubic centimeters. Now let's go ahead and construct our range for the volume. So if we were to take this number and subtract it by 24.5, that will give us 578.2. And if we were to take this number and add 24.5, it will give us 627.2. And that's going to be in cubic centimeters. So notice that the volume is definitely somewhere in this range. The lowest possible value that we got was 578.8, which is between 578.2 and 627.2. And notice our upper range, 627.151, is also in this interval. It's just under 627.2. So this is a good approximation for the volume of the sphere. So now that we have this information, we can calculate the percent uncertainty of the sphere. So first, let me clear away a few things. So the percent uncertainty is going to be the estimated uncertainty, which is 24.5, divided by the measured value in the volume, which is 602.7, times 100%. And that's going to be 4.0654%. So we could say it's approximately, if we want to round it, we could say about 4% or 4.1%. Now, there's a quicker way in which we can get the same answer, a shortcut method, if you will. So let's calculate the percent uncertainty instead of the volume, but in the radius of the sphere. So the percent uncertainty, I'm going to put R for the radius. It's going to be the estimated uncertainty, 0.07, divided by the measured value of 5.24 times 100%. So that's going to be 1.336%. Now, to get the percent uncertainty in the volume, given the percent uncertainty in the radius, it's going to be this value times the exponent 3. So notice that the volume is proportional to r cubed. V is equal to 4/3 pi r cubed. So if you were to double the value of r, the volume will increase by a factor of 8 because 2 to the third power is 8. So this 3, when dealing with percent uncertainty, it turns out that the percent uncertainty in the volume of the sphere is going to be 3 times as much as the percent uncertainty in the radius of the sphere. And we can see that if we do the math. So if we were to take this number and plug it in for the percent uncertainty in the radius of the sphere, and then just multiply that by 3, we're going to get about 4%. I got 4.008, which is basically roughly 4% if you round it. So even though you won't get exactly the same values, they will approximately be the same if you use the shortcut method. Now let's take a moment to explain why this works. Why we could simply multiply it by 3 based on the exponent. Now this is going to involve calculus for those of you who might be interested. If you're not, don't worry about it. Just know that you just got to pay attention to the exponent. So if you were dealing with a question, let's say involving the area of a square, which is basically s squared. If you want to find the percent uncertainty in the area given the percent uncertainty in the side length, the percent uncertainty in the area will be the percent uncertainty in the side length times 2, because the area is proportional to the square of the side length when dealing with squares. So just look at the proportionality, look at the exponent, and that'll tell you if you need to multiply by 2, 3, or 4, and vice versa. But now let's talk about why this works. Using calculus, let's differentiate that formula. dV, by the way, dV, you could think of it as the change in volume. They're not exactly the same, but they're very similar. So dV is going to be 4/3 pi times the derivative of r cubed. Using the power rule, it's going to be 3r squared, and then times dr, which dr you could think of it as, or approximately, the change in r. So we could say that the change in V is 4/3 pi times 3r squared times the change in r. And we could put in an approximate symbol here. So now if I write the ratio between the change in V The change in V would be like the uncertainty or the error in V. If I write a ratio between the change in V and V, that's going to be, the change in V is this stuff right here. So that's 4/3 pi 3r squared delta r. And then V is simply the original equation, 4/3 pi r cubed. So now let's simplify this. We could cancel 4/3 pi. So we have 3r squared. R squared is r times r. We also have delta r on top. And we have r cubed, which is basically 3 r's multiplied to each other. So we could cancel 2 r's in the top and the bottom. And so we're left with delta v over v is equal to 3 delta r over r. But we can write that as delta v over v is 3 times delta r over r. So now you see where the 3 comes from. Now I'm going to multiply both sides by 100%. So we have delta v over v times 100% is equal to 3 times delta r over r times 100%. Now think about what this means here. Delta v is, you could think of it as the error or the uncertainty. They're not exactly the same, but you could think of delta v as the uncertainty. So we have the estimated uncertainty divided by the measured value times 100%. So this whole thing is equivalent to the percent uncertainty in the volume. Here we have the uncertainty in r divided by the measured value of r times 100%. So that equates to the percent uncertainty in r. And then times 3. So that's why that particular formula works. So in this problem, if you calculate the percent uncertainty in the radius, all you need to do is multiply that by 3 to get the percent uncertainty in the volume, because the volume is proportional to r cubed.